Okay, so if p of n equals 3 to the power 2n minus 1, prove by induction that it's divisible by 8 for all n element n. Okay, so what we're going to do is we're going to do step 1, and that's going to be p of 1. P of 1 equals 3 times 2 to the power 1 minus 1, which is 3 squared minus 1, which equals 8. 8 divided by 8 equals 1. Hence, P of 1 is true, because it works for P of 1. Step 2 is going to be P of k. We're going to assume true. For P of k. Okay, and when we assume true for P of k, what we're going to get is P of k equals 3 to the power 2k minus 1. And we're going to assume that's divisible by 8. Okay, step 3. We're going to test P of k plus 1. We'll test P of k plus 1. What we're going to get is 3 to the power 2 into k plus 1 minus 1, which ends up with 3 to the 2k plus 2 minus 1. Oh, sorry, the minus 1 is a big number, not in the power, excuse me. So, in here and in here, and what we then get, we're going to separate out the, we have to separate out the little parts here. Okay, so we're going to leave out the 2k, so we're going to have 3 squared by 3 to the 2k minus 1. We're going to have 9 by 3 to the 2k, then all minus 1 over here. Now, what we need to do here is we need to make up P of k. So to make P of k, we can see that there's one of these here. Okay, so we break up the 9 into 8 plus 1. Okay, then we get 3 to 2k minus 1. Then what we can get here is going to be, that's 3 to 2k in brackets and the minus 1's over here. So we're going to get 8 times 3 to 2k plus 1 times 3 to 2k, which was 3 to 2k minus 1. This part here is divisible by 8, as 8 divided by 8 equals 1. This 8 on the outside is divisible by 8, and this is divisible, assumed divisible by P of k. Therefore, hence P of k plus 1 is divisible by 8 if P of k is true. Hence, by the principle of mathematical induction, P of n is true. Now, next one, step 1. So P of n equals 5 to the power 2n, 3 to the power 2n. So P of 1 is going to be 5 times 2 to the power 1 minus 3 times 2 to the power 1. Hence 5 squared minus 3 squared, 25 minus 9 equals 16. 16 divided by 2, 16 divided by 8 equals 2. You can say hence true for P of 1. Okay, step 2. P of k Okay, step 2. Assume true for step 2 is assume true for P of k. Okay. Now, assuming true for P of k is going to be P of k ends up to be 3 to the power of 2k minus 1. Okay, and we're assuming that that's divisible by 8. Oh, sorry, excuse me, guys. I got my numbers mixed up this time. My questions mixed up. It's actually 5 to the power of 2k minus 3 to the power of 2k. As we can see here, replace n with k. And we're going to assume it's divisible by 8. So we're assuming it's divisible by 8. Okay, step 3 is test P of k plus 1. Now P of k plus 1 ends up to be P k plus 1 equals 5. Now 2 times k plus 1 minus 3 times 2 times k plus 1. The answer would be 5 to the 2k plus 2 minus 3 to the 2k plus 2. Answer to be 5 squared by 5 to the power 2k minus 3 squared by 3 to the 2k. And then after that we're going to get is 25 by 5 to the 2k minus 9 by 3 to the 2k. Now when you look at this, guys, what we have here is the bigger number is 25, the smaller number is 9. So we're going to break 25 up into 16 plus 9 by 5 to the 2k minus 9 times 3 to the 2k. And what we're going to get is 16 by 5 to the power of 2k. We're going to get plus 9 to the power of 9 times 5 to 2k minus 9 times 3 to the 2k. Factorize out the 9, and we're going to get 9 times 5 to the 2k minus 3 to the 2k. And what this does is it's basically the same thing as P of k. Okay? And this is 16 by 5 to the 2k. So, the first part, and this is all P of k plus 1. The first part is divisible by 8. Divisible by 8, and 16 divided by 8 equals 2. And this part here is assumed divisible by P of k. So hence, I'll just use this here. Hence P of k plus 1 is divisible by 8 if P of k is true. Okay. Hence, by the principle of mathematical induction, P of n is true. So this basically means P of any number is true. Okay. Now, next question. Question 10. N squared plus 3n plus 2 is even, divisible by 2 for all n greater than or equal to 0 and element z. So guys, in this question, P of 0 is the smallest number, so we're saying P of n equals n squared plus 3n plus 2. We want to prove it's even, so I had to prove it's divisible by 2 for n greater than or equal to 0. That's why it's an integer, because remember, natural numbers only include 1, 2, 3, 4, 5. But by having an integer here, we also include 0. So 0 is the smallest number, okay? So, to start this off with step 1, we've got to test the smallest value in the sequence, okay? And the smallest value in the sequence is going to be P of 0. So P of 0 equals 0 squared plus 3 times 0 plus 2, and that equals 2. 2 is divided by 2 equals 1. So, hence, P of 0 is divisible by 2. Next, step 2 is assume P of k is true, or P of k equals k squared plus 3k plus 2. Now next, step 3 is to test P of k plus 1, and P of k plus 1 equals k plus 1 squared plus 3 times k plus 1 plus 2. And what we get here is going to be k plus 1 multiplied by k plus 1 plus 3k plus 3 when we multiply that out plus 2. And we're going to get k squared plus 2k plus 1 when we multiply all these out here. And then, once we've done that, we'll get plus 3k, and I'll just turn that into a 5. And then finally, we're going to get k squared plus 5k plus 6. Now, what I have to do when I get P of k plus 1 is I have to pull out P of k. Now what is P of k? P of k is k squared, 3k and 2. So I'm going to use k squared, I'm going to break that up into 3k, I'm going to break that up into 2, and then over the other side I'm going to put the other 2k, and the other one is 4. 2k plus 4 over the other side. Okay? And then we can say the following. This part here is assumed to be divisible. Assumed divisible by 2 by P of k. And this one here is divisible by 2, as it's the same thing as 2 times k plus 2. Now you can change your 2k plus 4 into 2 times k plus 2. Hence 2 divided by 2 equals 1. Now you've proved that both parts of P of k are divisible. So now it's just a matter of writing down the formal part of the proof. So hence P of k plus 1 is divisible by 2 if P of k is divisible by 2. Hence, by the principle of mathematical induction, P of n is true. Okay guys, so in today's we've done 10, we've done 10, we've done 9, 7, 9 and 10.